Now we are going to investigate topological semimetal, including the wire and the Dirac semimetals. Because they are semimetals, they are metallic. We don't have a band gap. Actually, this parity criteria, well, we cannot apply it anymore. But we can still use other methods to understand the band structure. For example, the band inversion and Wilson loop. The most famous wire semimetal, actually the first one discovered in experiment, is tantalum arsenide. This material looks a little complicated because it breaks inversion symmetry. It is composed by Ta and As, two elements. Because it breaks inversion symmetry, it has time reversal. Then the band structure has a lot of splitting. Actually, the real band structure from DFT you see actually is kind of complicated. Here, the dotted line you see is without spin-orbit coupling. You see the valence and the conduction band, they will cross each other. This crossing actually not only on these 2 points, and this crossing will form a ring in this three-dimensional space. Like here, this gapless point form a ring, these green rings. There are many rings because this material has several mirror planes. And in each mirror plane, there are 3 rings, and therefore in total, there are 6 rings. But as long as we include spin-orbital interaction, this is an intrinsic interaction in the material, then this nodal ring gets immediately gapped out. Looks like it becomes an insulator. However, because it's gapped out, actually the band at the same time also gets split. We don't have the spin degeneracy anymore. This is the consequence of inversion symmetry breaking. And then actually near the nodal ring, the band will touch somewhere else. The touch point only some isolated points. They are not rings anymore. Actually, these touch points, as indicated here as these blue and the red points, actually in 3D Berlin zone is here. They are still somewhere nearby this nodal ring. And in other words, actually, the nodal ring is a consequence of band inversion. And about these points, it comes from spin-orbital coupling, the band splitting. Let's zoom to the single point. Actually, the point always comes in pair, and like in the band structure here, the valence band and conduction band always cross each other in pair, and each point actually we call it a wire point. But what is a wire point? First, it's a single point, the band touch each other. Near this point, the band disperse linearly in 3-dimensional direction. And in other words, actually, this is a 3D graphene band structure. Yeah, actually, this wire point has a special topology. How do we identify this topology? We can take a sphere including this wire point. For example, here, on this sphere, we know the band structure has a gap. It's an insulator. Therefore, in this case, we can still use this Wilson loop technique. For this sphere, we take every loop as the charge center. We calculate the theta, but we count all these loops, and we have a dispersion. Yeah, the evolution is like the quantum anomalous Hall state, and this tells us this wire point is a monopole. It has a monopole charge +1. If the dispersion is opposite from 1 to 0, it has a negative topological charge. And actually, these pairs, this green, this blue, and red pairs, they always have opposite topological charge, or we call it chirality, opposite chirality. This wire monopole has a consequence, is the surface from arc, has a special surface state. Now, we talked about bulk, then we will go to the surface. On the surface, as we learned how to calculate surface, we need a slab model. In this slab, we have top surface, bottom surface, but different from the bismuth selenide example. Bismuth selenide has inversion symmetry. However, this material breaks inversion. The direct consequence is the top surface and the bottom surface will be different atoms. They are either arsenide atom or tantalum atom. Since they are different atoms, then the details of the surface potential will be different, right? Then we have a reason to believe their surface states will be different. Maybe they have same topology, because topology is a property of the bulk. They share the same bulk, they share the same topology, but the details can be different. Then how different? Actually, this is the calculation, just the DFT calculation for this slab model. The red color in the band structure, you see they are surface states. They are surface states projected to the arsenide surface. This is surface state projected to the tantalum surface. If we plot the Fermi surface in the Berlin zone, the Fermi surface is the energy control across the energy zero, and we will see very different Fermi surface. Actually here, where is the Fermi arc? Where is the topology? Actually, here is the Fermi arc, this spoon shape. This Fermi arc, they connected these wire points, start from one and end at the other. These two, they have opposite chirality. They start from one monopole, end at this opposite monopole. Now let's summarize for the wire semimetal. And as we did for topological insulators, we can always start from the bulk band structure. We identify the band inversion. Actually, band inversion tells us where the nodal ring is. Near the nodal ring, there will be wire points after applying spin-orbital coupling. As long as we identify these wire points, we can go to the detail, identify the topology, this monopole structure. And as a consequence of wire points, we can observe Fermi arcs. This Fermi arc will connect these wire points on the surface. There is another topological phase called Dirac semimetal. Actually, we can understand Dirac semimetal as two degenerate copies of wire semimetals. That means in the band structure, we'll observe the degenerate wire points. And here a wire point is two-band crossing. Therefore, Dirac semimetal will be a four-band crossing. We can identify these wire points. We can also identify the topology of the Dirac points. And then for the similar reason, we can believe there are surface Fermi arcs. Just now, the Fermi arc will be two copies. Then in addition, you can always find these input files, original data in this paper and in this database, and play by yourself. Good luck.